Okay, now go to the last topic. Actually, two methods. The steepest descent or gradient descent and conjugate gradient. And both of them, before we learn both of them, I have to review gradient, because it's very important for the gradient method. Now we start with the function f. Now the function f, the input vector, Rn represent vector. Input of this function is the vector, n component, and output scalar, the real number. So we can write f, fx, and this term is the scalar. And the function that we will focus here is what is called the quadratic function. The quadratic function is defined by this. This is quadratic function, x, column vector, and this is scalar. Now b is column vector. Now b transpose become row vector, and this is scalar and some constant here. Now in vector calculus, the operator here is called the gradient. Now when you can think of the differential operator. Now when you take the gradient, now the gradient of the function will be this. Now it's you have to review vector calculus a little bit. This is the gradient, and notice that the gradient of function f. Now you see that function f returns scalar, but the gradient of function f return vector. Here's the vector. Now when A is symmetric, A equal to A transpose, now we can combine the two terms. Now the first two terms, and we get ax minus b. Now for this particular function f, the quadratic function. Now for quadratic function, we are looking for. Now you can see that if gradient is set to zero vector, the vector x that cause the gradient equal to zero vector will be ax minus b equal to 0. Is actually the solution of the linear system ax equal to b. Now you see the relationship between the gradient and linear system. Now we start with the quadratic function. Quadratic function defined by this first equation. If we take gradient, we get this expression for symmetric metric. Okay, A. Now and x that minimize the gradient to 0. That makes the gradient to 0. Now in optimization, now we're gonna walk into the optimization. Now we're gonna walk into the optimization method. Now this is the first, probably the first time. Okay, we're gonna walk. Optimization means that you can think of the function of one parameter of Now we get derivative equal to 0. It can be maximum location or minimum location, right? Now, but in a case of multiple unknowns, now we look at the gradient. Now the gradient contain the partial derivatives. Now I will explain the gradient later. The objective here is to show that the solution x that make the gradient equal to 0. Now this is the optimum solution for this problem. Now is the same as the solution of linear system. So the strategy for the gradient method is to look at the gradient of the quadratic function. Like we will go back. We will come back here later. Okay. Let me explain the gradient. Now you have the function f. For simplicity, we use the case of two unknowns. Now x has two components, f to r. Now when we plot f of the vector x, we can plot in the vertical coordinate set, and f will show you the surface. Here's the surface defined by vector f. The function f. The height of the surface at a particular coordinate x1 and x2 represent f. We plot. Okay, the gradient operator here involve the partial derivative. Partial derivative f with respect to x1, partial derivative f with respect to x2 up to in mathematics we call if the gradient return vector, we call vector field. Because at a particular point you have vector. Now vector has n components defined by partial derivative. Now the first component here, the second component, this is the component of the gradient. We call the vector field. This is the gradient in case of two unknowns. Vector x has two components. Okay. Now the output of gradient is the vector, and it's the function of coordinate. So we call vector field. And it's interesting to know that in the first method, we're gonna use the gradient as the direction for the search, for our search, for the optimization. The vector field in the direction of greatest increase with the if we are at particular point and you don't want to go down the hill. What we should look is the direction that of the gradient. Let me go back here a little bit. Now this is the gradient. Now if f is a quadratic function, the gradient is here, right? Okay, x minus b. Now we have the linear system ax equal to b. Now if I define the difference between b and ax, now defined by the vector r. Now vector r is called the residual vector. Now if x is our solution, the residual vector should be 0, right? Now this is called the residual vector. Now let's see the definition. Residual vector b minus ax, and gradient ax minus b. gradient ax minus b. So you can think that you will find that the residual vector is the negative of the gradient. Now we will make use of this definition later. Now we can prove that if matrix A is positive definite, now our solution will be the minimization of function f. Minimization of function f. Okay, let's see the proof. Okay. Now let's see, it's the error vector. Now is the error vector. X star is the true solution. Vector of true solution. So f at x, right? This is x. You can write x star plus e. F at x. Now we can write that x star plus e. This is our original quadratic equation, right? You can look and when we get the last equation, what happened? The last equation. This is the function at the true solution, and this term, if matrix A is positive definite, this term will be positive, right? So what does this proof tell you? It tells you that the function at any point will be larger than the function at the true solution. It will be equal to the function at true solution when the error is 0. And that is the minimum point. When the error gets down to 0, you get to the minimum point. So that's why we call the minimization. When A is positive definite, this term is always positive by the definition of positive definite. Multiplied by any non-zero vector. It will be 0 only when E is 0. And for that case, X becomes X star. And X would be your true solution, the minimum point. If A is positive definite, the second term is always positive. So we can think that solving the linear system is equivalent to finding the global minimum of f. Okay. Minimization. But actually, the optimization involves the general function. We will talk about that later. But here, we learned that if the function is the quadratic function, when you take gradient, you find that the vector x that make gradient equal to 0 is actually the one that satisfies the linear system. The quadratic function defined by this one. Okay. Okay, now you learn gradient. The first one, steepest descent. It's an iterative method, so you have to begin with the initial case. Let's say x star. I'm sorry, x0. X naught 0 initial case. And the strategy is that now we're gonna go to the actually this is not the quadratic function, this is a general function. You can see that f cosine is the general function, but quadratic will be like the bowl shape and the quadratic. This is the quadratic that we quadratic. But for general, if you want to apply to the general function f, you can do this way. You have the function f, and you want to search. You want to search for the optimum solution choose an initial case, and each iteration we take a negative gradient direction. Now you have the initial point. This is the case of two components, two unknown. At this point, you start with this point. You evaluate the gradient at this point, and you use that direction to move to the next location, next solution. Take the negative gradient. What is the negative gradient direction? The direction of residual vector, right? In our case, in our quadratic function. But for general function, you can determine the gradient from the from here. Take partial derivative. You calculate the gradient, and you go to the negative gradient, opposite to the gradient, the negative gradient. Okay, this is the 3D plot, and this is the 2D plot of the contour. Now, contour means that when in survey, when you learn survey engineering, the contour line, the line that have the same height, right? So the contour line here represent the same function value, and the same function value. Now this is the contour line. Now with the initial case, now if you look from top view, now you're gonna see, and you draw the contour line. Now you start with some point, and you find the gradient. You go to the negative gradient direction, and you stop at some point. This is your new solution. And with iteration, with the new iteration, you go to find the gradient at this point. The gradient is a vector, phi vector. At this location, calculate the gradient. Now go to the negative gradient and stop. Now, interestingly, the search direction. Now this is the search direction. Now for every iteration will be perpendicular. Now the current, this is the current iteration, and the following iteration will be perpendicular. That's a proof. I will not explain the proof right now. Just show you the idea of steepest descent. Okay, start with this point and go perpendicular until we go to the optimum point. Now this is the idea of steepest descent. Now this is a complicated function f. In our case, we have the quadratic function, and actually we do not have to find the actual negative gradient direction. What we do is to find the residual vector, because we know we don't care about function f, right? What we know is a and b, right? We are given metric a and right hand side vector b. We don't have to formulate this one. We don't care about f. This is just the theory things. What we are given is metric a and right hand side vector b. Okay. Now if we are given metric a and b, vector b like this, we can write that our function f, quadratic function defined by this, will be here. F is actually, if you do the minimization of to make f become the minimized value of f, that location, the solution will be the solution of linear system ax equal to b. Ax equal to b. Okay, what is this? A solution of this linear system. determinant of A 0 or not? Not 0 is the determinant of A is 20. So this is our system is our example here is non-singular, and solution is we have the homogeneous system. 0 vector, right? We know that the solution is the 0 vector. So we know that the solution is here. Okay, just for your reference, that we have the solution, the true solution is actually at origin. Okay. But we're gonna find the solution by steepest descent. Okay, we are given f. This is x1 coordinate. This is x2 coordinate. X1, x2. Oh, okay, it's shown here already. The contour line are given. The contour line are given here with different function value. Let's say that the blue line means that on the blue line at coordinate along the blue line here, function value is equal. The function value are same. Okay. Now, if you begin with the initial case, our initial case is 3.22 and 1.39 the coordinate here. 3 and 1 point. Okay. And you can find the gradient of f. Take a partial derivative with respect to x1, you get 2x1, right? With respect to x2, you get 10x2. And you can find the gradient, and then you can plug in. Now you want to find the gradient at this particular point that at the initial case. Now this is your negative gradient. Let's go this way. In the minus in the x-axis, minus 6.4 and minus 30. This direction, you go this way. This is the direction that you think is the steepest direction at your current point. The negative gradient is the steepest direction. Now we can prove that. I don't show you the proof. But I have in the supplement video for your reference. But here we're gonna talk about the procedure to make to save our time. Okay, so the first iteration, you start with initial case and you find the negative gradient. The question is, when do we stop? Before we go to the next iteration, where do we stop? The black line represent the direction. The question is, what should be our step size to stop? We're gonna now we can prove that the stopping point occur now when the surge negative gradient at this top point is perpendicular to the current. And this is the new surge direction is perpendicular to the current surge direction. I don't show you the proof. But trust me, that is perpendicular. The proof will take time, and I will prepare the supplementary video that we can prove that. You can say that we can prove that the minimum along the line will occur at the blue line, where the negative gradient at this point, and the negative gradient is the surge direction. The blue line here is perpendicular to the previous surge direction. Now at this point, trust me, okay? Or perpendicular in mathematics we can call it orthogonal. Now orthogonal to the previous search direction, and the new point is given by this the coordinate here. And we're gonna go to this search. Now this certain iteration is stop when the gradient at some point, pink point. Now if you find that the pink point has the gradient perpendicular to the blue, the blue line, which is the gradient in the previous search. And we're gonna go to the zero, the origin by this strategy. And here's the algorithm. The algorithm here apply to the general function f. But if we consider the quadratic function, instead of finding the negative gradient, now we find the residual vector. Now b minus ax residual vector. Now the search direction now will be the residual vector. Now the right hand side vector be subtract by a x. Now for the first iteration, now you begin with x0. So the residual vector r0 is b minus ax0. And you determine the step length. Now we have the proof that gives us the first equation. The step length will be transpose r. Now this is a scalar. The column vector, when we transpose to get the row vector, the product of row vector and column vector is scalar. This is the dot product. Okay, and this is also the scalar. So we get the step length from this equation. There's a proof. That's a proof that with this step length you get the orthogonal direction, or orthogonal in the search direction vector, the search vector, negative gradient, and actually we use the residual. So step 2, we don't have to compute the step size. Now you can use this formula. And with that, now you can update. Now this is the iterative scheme, the iteration scheme for steepest descent. Now the new solution is the current solution or the old solution. Now update by search direction and step alpha. Step alpha. Okay. And you continue until the convergence is satisfied. Continue until convergence satisfied. If it's not, you go back, repeat, calculate the new residual vector, calculate this, the new one. But this is not good in terms of the computation. That we in the our algorithm, now we're gonna use this equation. It can be derived. It can be derived. This equation very simple, because the product here already determined when you calculate step length before, so you don't have to compute this product again. You don't have to avoid computation. This is the preferred formula. In the value same, you can use this one, but it's not convenient because you have to, with the new value, you have to calculate the product to get the new search. But here you just subtract. This is known. this is known, right? You just subtract R by this product that you calculate when you determine the step length. Okay, hand calculation a little bit to show you the method, steepest descent in our metric A and B. And we don't care about F anymore, right? We don't care about function F. What are the function? What we care is A and B. And we know that the negative gradient is our residual vector. Okay, we assume the initial case, this is the hand calculation. First iteration, you compute R0, the residual vector B minus X0. Now you do the metric vector multiplication and you get R0. And then you compute AR0. Now because AR0 will be here, compute AR0, do hand calculation, get vector. Okay. And to get alpha, you need transpose R divided by R transpose AR. R transpose R will give you scalar, right? And R transpose AR, AR here. So you calculate alpha. And notice that the dot product of residual vector is actually the square of the Euclidean norm. So if you find the norm of the residual vector, the norm, remember norm is the B minus AX, that the norm of B minus AX0 is here. This is the norm. We may use this as into the stopping criterion. Okay. Keep in mind that this is the norm. Now, if X0 is your solution, what would be the norm? 0, right? 0. But here it's saying that your initial case is not the true solution because the norm of the residual vector is not 0. Anyway, now let's get back to alpha. Now you get alpha, and then you apply the iterative formula. Now x1, the new solution, the current solution equal to the current solution plus the search direction vector and the step length. Now you get the update solution, and you finish. Now you are ready for the new iteration. Now, but before the new iteration, now we need R1, right? R1, the new search. Now you can complete R1 here. Now R1 is the R0. Now subtract by alpha AR. You get R1 here. And notice that the norm of the new solution is 5.44 and not 0. Okay, the second iteration. You know that R1 already from this calculation, R1 that you want to use in the update solution here. This is your solution. This is your target. You need R1 already compute, so you need alpha. You calculate alpha. You need AR alpha. Require AR1 here. Require transpose. Now you get alpha. Then you can update your solution. Your solution become here. And compute the new residual and the norm. Okay. And after 13 iteration, with calculation will be very tedious. You get 0, 0, and the norm goes to 0. This is hand calculation. we have about 5 minutes. Now let me implement a very simple formula without proof. Okay, very simple formula without proof. Yeah, let me call the function x steepest 6, 7. I put A and B. Okay. Without any comments, MN want to make my code short, size A. And input for this particular problem, let we use x0. X0 is our initial case 3.22, 1.39. I'm going to show you that it will use 13 iteration by our hand calculation ES 10 1 to the power of minus 6. 10 to the power of minus 6 will be our tolerance. Not sure if this is the one that we use or not. Okay. And the maximum iteration in case that we do not converge maximum number of iteration. Okay. And we're gonna start the iteration. Similar to the Jacobi, and I want to have my update solution stored in the matrix X. The first column initial case, the second column for the next solution, and so on. So this is the first column. This is my initial case, and I compute the residual. And this is my search direction B minus A, the input, and X 0. Why do we have no, not sure here. What is this? Okay, and the search direction is so in the future I will slightly modify steepest descent, and I get the conjugate gradient, the more effective algorithm here. Would say that this is the search direction vector. Here we use the gradient. Okay. And then we go to the for loop that will fill in my solution in the from the second column to max IT. A multiply R, in this case AD. This is a temporary vector W, get alpha R transpose R prime times So this is the scalar divided by D R transpose W. W is AR. This is actually transpose AR. Okay, we get the step links, and we can update the solution X K plus 1 go to X at column K, and this is the previous solution plus alpha multiply D. D is actually residual vector, and the I calculate the now before I do the calculation, I want to keep the own residual, and then I find the new residual alpha. Now you can refer to the formula that we have, alpha W, I'm sorry. Now we have the residual here. In the first iteration, you get the residual from the here. Okay. We store into assign to the own value, and then you update the residual vector by this. Okay. And check the norm. If norm of R2 means that we consider the Euclidean norm. ES we break. This is the early termination. It can, if the stopping criterion is satisfied, if we're gonna run for loop until the maximum iteration, but when whenever the stopping criterion is achieved before the maximum iteration, we can get out of the for loop. Okay, can get out of the for loop. And with the end here, we change the search direction. And I want to show you the iter. This K. Iteration K. I can have iter as my output to see the iteration. Iter. Okay. And I can plot my solution to see how my solution progress. Okay, save. Steepest 67. Okay. Okay, let's define our metric A. In the calculation is okay. 2 0 0 10 and B, and we know that the solution very simple. We have the solution is at the origin, right? This is the solution. But if we start with the initial case, similar to what we have in the hand calculation, yeah. Okay, let's see what happened. We spent 29 iteration. Why do we have 13 here? 13. Probably because my stopping criterion is very strict. It's a 10 to the power of -6, right? If I decrease to like power 2, try it again. 13 iteration. Probably the election node use the stopping tolerance 10 to the minus power 2, 0.01. Okay, so see what happened. Size of my solution vector x 2 by 14, 2 row, 14 column. The first column is our initial guess. Right? And the last column, what is last column? Column 14. It means that we 14 at the end of 13 iteration. After 13 iteration, this is my solution that very close to zero, to the true solution. Required. Here is the steepest descent. Now we begin with initial case, and let's show. Let me show you the figure. I have to stop share screen and then show you the plot. This is how my solution progress. Now we have two line represent the two unknowns. Now when iteration increased, you can see that it converges to zero. This is the first unknown. Now the blue line represent the first unknown, and the orange line represent the second unknown. Okay, you can see that converge in this case.